Thank you very much indeed. Our next speaker is Marc Saunders. Marc is the Group Marketing and Technology Director for e2v. Now, e2v may not resonate with you perhaps as well as Marconi, which is the heritage name behind the company. So he comes from a great tradition of innovation and technology. And he's also speaking in his capacity as President of Space Imaging. And he will try and unlock a question about the mysteries of the universe. So over to you.
Thank you very much, Chris. Okay, so I'm going to talk to you about how some of the technologies that we are developing are helping mankind to unravel some of the mysteries of space. I'll start by talking about some of the technologies and then move on to talk about how those are being used to enable greater understanding and real breakthroughs in our understanding of the nature and the origin of the universe. There we go. So firstly, just 30 seconds on e2v. We're a technology company that specialises in high performance and high reliability solutions for demanding applications. We partner with our customers to improve, save and protect lives. We're a UK PLC headquartered in Chelmsford in Essex, employing around 1,600 people, with about 85% of our revenue is generated overseas. So that's us. The bit that I'm here to talk about today is our space imaging business, which I lead. And in space imaging, we provide mankind's eyes to see and to understand the universe. We make super precise and high reliability cameras that can withstand and perform reliably in the harsh space environment that Matt was talking about. We've been doing this for over 30 years, and we've been trusted to deliver solutions for over 150 space missions. So it's something we've been doing for a long time. So I'm going to talk firstly about some of the differences between all the technology actually that Matt was talking about, the commercial off-the-shelf stuff, the stuff that's in your mobile phone, and some of the stuff that we do, which is perhaps at the other end of the spectrum, I guess, from what Matt was talking about. So what are the differences between the camera that you've got in your iPhone and what we're putting up into space? Well, firstly, there's price, about 20 million quid, actually. So, but why is that? You know, why is there that enormous price difference? And really, it's because we're doing a lot more than taking a holiday now. You know, the applications we're doing are very much more demanding. A few things. Firstly, space is big, seriously big, as we'll see. And so therefore we're looking at things that are a very long way away. They're often very faint. And so therefore our camera has to work really hard to see them. Also, we're looking to do more than just take a picture. We're actually looking to analyse what we're looking at. So we're looking at colour, we're looking at spectrometry, we're often looking at position and motion, and we're looking for differences with previous observations so that we can see things moving and changing. So actually there's a huge amount of more information we're trying to extract than just a pretty picture for us to look at. And then finally, there's the environment. You know, Matt talked about it. It is an aggressive radiation environment in space. The further you get outside the Earth's atmosphere, the more the solar wind with the high energy particles and radiation batters the electronics that we're putting up there. So we have to design them to withstand that. We also have to, they also have to withstand massive temperature changes. If you've got a satellite orbiting the Earth, as it goes into the shadow of the Earth, it drops a lot, hundreds of degrees centigrade. So they have to withstand that. And also they have to withstand the launch, which itself can be pretty violent. You know, there's a lot of acceleration and vibration when you're taking off. So it does require, for these big instruments that we'll look at, some really very specialized technology. So its size, we tend to be talking in gigapixels rather than megapixels. So some of the cameras, and we've got an example of one on our stand outside, you know, they are very large devices. There's also sensitivity. So we're looking often to be 10 times or 20 times more sensitive to light and more efficient in turning light into signal than an iPhone camera would be. And finally, there's the toughness, the fact that it's got to withstand both the radiation and the vibration. So that's where your £20 million goes. Okay, so that's enough about the technology. Let's actually look at what is it that we're looking at. Mankind's exploration of the universe really starts in our neighbourhood, the solar system, and that's driven by our desire to understand and in the future maybe visit other worlds. And so exploration within the solar system tends to be about sending spacecraft to other places like Mars, like comets, in order to understand them more, and perhaps land on them and actually take a look around and see what's there. So that's one one area that we work in. The other area, of course, is where mankind looking beyond our solar system, looking to the stars, looking to galaxies that are light years and billions of light years away even. And so that's a very different type of challenge. There, we're never going to get there, unless Einstein was wrong. We're not going to get to the stars. But what we can do is look at them with ever more detail and precision. And so we work in both of those fields, and I'm going to talk about both of them in the next few slides. So let's start close to home. Let's look at Mars. This is the closest planet to Earth, of course, and it's certainly the next one that we'll walk on. I think 2034 is the date, I believe, Chris. That's right. Yeah.
Guaranteed.
NASA's saying they're going to get a man on Mars, so it's 20 years away. It's within most of our lifetimes, hopefully. And this is what Mars looked like with the best Earth-based telescopes in the early 1960s. This is the best we could do. And back then, we were thinking those dark areas were forests, they were maybe seas. I mean, how wrong we were. Now that we've been there more recently, we realised that our knowledge from that kind of imagery was really primitive. And then we went there. So in 1965, Mariner 4 flew past Mars for the first time, and this was the image that was taken. It's not wonderful, as you can see, but it was the best we had at the time. The digital technology back then was really primitive. But we got a bit more knowledge, and then in the mid-70s, we actually touched down on the surface. So this is NASA's Viking missions, landed on the ground. This is one of the first images from the surface of Mars. And you can see it's a pretty barren and lifeless place. We didn't find any life, and it looked pretty dry and dusty. But we didn't give up. This is an interesting one. This is an e2v camera that's looking down at another spacecraft, a lander from the Phoenix mission, landing on the surface of Mars, trailing its parachute. So that little white blob you can see in the middle there, that's the parachute, that's the spacecraft. It's the first time one spacecraft had ever filmed another landing on another planetary body, so it's kind of fun. And then the following year, again, another e2v camera on NASA's HiRISE mission actually mapped the whole surface of the planet so that we got to see the geology. We understood where the mountains were, the valleys, and got much more detail. And that allowed us to look for areas that may have been formed by water on the surface of the planet, and maybe from volcanism, things like that. It also allowed us to look for good places to land, but interesting places where you might see quite a lot of geological features of interest. And of course, you'll all be familiar with this fella, I guess. You've seen it in the press over the last couple of years. The Mars rover, it's about the size of a family car, so it's a reasonable size space vehicle that has been roaming around Mars. It's moved several miles, and its mission, it's got a lot of cameras on board. It's looking at the surface of the rocks. It's drilling in. It's zapping rocks with laser beams, turning them into plasmas, which we can then image and see what was in that lump of rock. So once this mission is finished, you're going to see tire marks all over the surface, and also little scorch marks where it's been zapping rocks to see what they're made of. And so its mission really is to see whether life ever could have existed on Mars. We don't think there's any life there now. What it's found actually is, yes, some of the building blocks of life are present in the soils of Mars, and it's also found some evidence that water could have been on the surface, smooth rocks that would indicate flowing fluid that had shaped them in that way. So, quite interesting stuff. No little green men, though, I'm afraid. No little green men. Okay, and it even found some time to take a selfie, as you can see. Okay, so moving into a different planetary body. Again, some of you may have seen this on the television recently, and you'll certainly see it next month. So this is Rosetta. Rosetta has been on a 10-year mission. It's travelled 4 billion miles. It's slingshotted around the Earth 3 times, around Mars once, to basically catch and then land on a comet called 67P. It's got a long name as well as that, but we'll call it that. So it's been up there for 10 years. It's now in orbit. It's been mapping the surface of the planet, the surface of the comet, trying to understand a good place to land. And next month, this lander over here, which is about the weight of an adult man, about 100 kilograms or so, will land on the surface, lock on. It has to clamp on pretty tight because there's not much gravity to cling on with, and then drill into the surface. So why on earth are we doing this? Well, one of the theories is that you're probably aware that comets are made of ice, and that's what makes the tail as they approach the sun. Well, one of the theories is that that's where the water on Earth came from. Was in the early days of the solar system, those comets were crashing into the Earth and actually depositing that ice, which later formed the oceans and all the water that we have on the planet. Another theory is that actually some of the building blocks of life, amino acids, may also be present on comets, and that could actually be where both water and those building blocks came from. So, in other words, comets could have played a critical role in the development of life on Earth. So what we're trying to do with Rosetta is understand actually what they're made of. Do some of these things exist? Are some of these theories true? Or have we got to think again? So interesting stuff, and you'll see that on the 12th of November, that lander is due to touch down on a comet it's about 500 million miles away whilst it's doing all this. So you can imagine the communication to and fro takes a little while. Okay, so let's look a little further afield. I said earlier on that space is unimaginably huge, and it really is. We, of course, have our galaxy, the Milky Way. We're actually in the middle of it, so it's quite hard for us to see our galaxy in total. So this actually isn't our galaxy lying a little bit here. It's actually a neighbouring galaxy that we think looks like the Milky Way. We live, of course, on a little blue planet orbiting in a solar system around the Sun. Our Milky Way has about 400 billion stars within it. And there are maybe 170 billion galaxies like that in the universe. It kind of makes you feel a bit insignificant, doesn't it? So let's look at how do we know more about these things? What are we doing? And we talked about Hubble earlier. Hubble was the world's first large space telescope. And the reason that it was so important is that it allowed us to look at the stars without the atmospheric turbulence that we get when looking at them from Earth. So we can see with such clarity that we can never do with an Earth-based telescope. So it was a really important breakthrough in our understanding of the universe. And it's been through a number of upgrades. It's actually been in operation for 20 years now. And e2v was involved in an upgrade in 2009, and you can see this sensor on our stand outside. It was an upgrade to one of the key sensors that allowed, it actually corrected for some errors that there were in the mirror, and allowed us to get even greater clarity to some of the amazing images that Hubble is famous for. And that's Sandra Bullock doing the repair. Should have stepped in. So just imagine, if you will, holding your arm out at arm's length and separating your fingers by a millimetre, okay, and then looking at the night sky through that gap. If you look really hard, you might see one star, possibly, if you're lucky. This is Hubble doing exactly that, looking really hard. Hubble can look much harder than we can, of course. And what you're looking at here, all of those blobs of light there aren't stars, they're galaxies. So each of those blobs of light has hundreds of billions of stars within it. There's actually 10,000 galaxies visible in that tiny patch of space. That's 1/30 millionth total night sky. It kind of gives you a sense of our insignificance. Okay, so that's some of the stuff we're seeing. Here's another sort of fantastic image. This is the Butterfly Nebula. So this is a gas cloud, essentially, that stars are forming from. And actually, this next image here is an image of stars forming in the Crab Nebula. So this is stars actually, the gravity pulling that gas into bigger and bigger clusters, and eventually they ignite. They get big enough to ignite and form stars. And so that's what's going on in this image. And this final one here is a very rare shedding star. It's actually a million times brighter than our sun. So not a great place to choose for your summer holidays. That is a serious sun protection factor if you get the sunlight there. Okay, so I'm going to talk now about another mission. And again, this is you can see some of these devices outside. Gaia is a mission that was launched last year. It's just become operational in the last few months. And it's got a very special job to do. It's actually going to provide a 3D map of our galaxy, the Milky Way. So it's going to look at about 1 billion stars. It's going to look at them over several years and observe their position and how they move. So it's going to give us that 3D view of our galaxy and what's happening, how things are changing. So we'll be able to rewind from that and speculate how the galaxy may have been formed in the first place. And it'll also allow us to fast forward to see, well, what's going to happen in the future and how's it all going to end in a horrible fireball. So we'll get that view, and it's going to be a really important underpin for our understanding of how galaxies work, what's happening with dark matter and how that affects things. It's going to be really fundamental stuff. Gaia features the largest camera that's ever been put into space. This is one of these £20 million cameras we're talking about here. So it's about the size of a flat screen television. It's a gigapixel camera. It has sufficient precision to spot a coin on the surface of the moon. But try doing that with your iPhone. Sorry, Matt, but you're not going to be able to do it. So it really is the very top end of what mankind is capable of in terms of imaging. And finally, looking forward to the future, Plato is the next big thing. This is another European mission. It's actually going to have a 4 gigapixel camera in it, so even bigger than Gaia. And what it's doing is planet hunting. PL stands for planets. And what it's looking for are planets that are in the Cinderella zone, that area where they're orbiting around the star and they're not too hot, not too cold, the right kind of temperature for water to exist in liquid form on the planet, which is the right kind of conditions for life. So it's going to go out there and survey the heavens and try and find many more of these planets to try and understand how common a planet is Earth, how many others are there out there that could support life, and maybe there are other people out there looking back at us doing exactly the same thing. Okay, so what I just wanted to finish there. We really are in a golden age, I think, for space exploration at the moment. There's a lot of big missions, a lot of exciting things happening. There's actually a lot of new countries coming into the space community as well, and a lot of collaboration internationally on new space missions. And we at e2v, what we're doing is enabling that with innovative manufactured products that are designed and manufactured here in the UK. So, thank you very much.